Welcome to Ito Analytics, the leading platform for providing volatility data and option analytics. This is Chapter 3 of Option Tutorial Series. We will cover option Greeks in this chapter. What are Greeks? In short, Greeks are sensitivity of option price with respect to different pricing parameters. Understanding Greeks allow traders to assess and manage risks as traders can estimate how market movements affect option value. More importantly, option Greeks can help traders to formulate option trading strategies by choosing optimal tenor and strike that fit the investment purposes. There are four main Greeks traders need to understand before trading options: delta, gamma, vega, and theta. Each of them measure different sensitivity. Before going into Greeks, we need to talk about an important concept in option. Option price has two representations. First one is dollar term, which is the absolute dollar amount of an option you see on trading screen. Second one is percentage term, which is option price as percentage of current spot. Percentage prices give traders better idea in comparing options across tenors and strikes. First Greek is delta. Delta measures how option price change with respect to underlying spot change. If an option has 50% delta, that means for $1 increase in underlying price, option price will be increased by $0.5. For example, assume we have a 1-month $105 strike call on an Apple. Option price is at $2 and delta is 25%. Apple is at $100 now. If Apple goes up to $101, then option price will be $2 plus $1 change times 25% delta, which is $2.25. There are some important property of delta we need to notice. For call option, delta is always positive and lies between 0 and 100%. This is because call option always increase when underlying spot goes up. For deep out of the money call, delta is very close to 0 as underlying change won't have impact on option value anymore. For at the money call, delta is around 50%. We can imagine the payoff is composed of 50% of underlying. For deep in the money call, delta is close to 100%. From payoff diagram, we can imagine that holding call option is similar to holding the underlying directly. $1 increase in underlying price translate to $1 increase in option value. Therefore, delta is 100%. For put option, delta is always negative and lies between 0 and minus 100%. This is because put option value always increase when underlying spot goes down. For deep out of the money put, delta is very close to 0 as underlying change won't have impact on put value anymore. For at the money put, delta is around 50%. For deep in the money put, delta is close to minus 100%. From payoff diagram, we can imagine that holding put option is similar to short selling the underlying directly. $1 increase in underlying price translates to $1 decrease in put value. Therefore, delta is minus 100%. It is very important for traders to understand delta. It is the primary Greek of option, and it measures how option value changes when underlying spot changes. Delta can also be used as an estimation of probability of option expiring ITM. For example, delta 50% means 50% probability for the option end up expiring in the money. Next Greek is gamma. Gamma measures the sensitivity of option delta with respect to underlying spot. Gamma of 5% means 1% increase in underlying spot will cause 5% increase in option delta. For example, if we have a 1-month call option on Apple with strike $105, delta of this call is 25% and gamma is 5%. Apple is at $100 now. If Apple goes up to $101, then the delta of this call option will be 25% original delta plus 1 times 5% gamma, which is 30%. For deep out of the money option, gamma is roughly 0%. Movement of underlying won't create any change in delta as delta is near 0% in the deep OTM region. At the money option has the highest gamma because delta change a lot when spot is fluctuating between ITM and OTM. For deep in the money option, gamma is also 0% as delta is near 100% regardless of spot movement in deep ITM region. For both call and put, gamma is always positive. For at the money options, shorter tenor ones always have higher gamma. Gamma is important in the sense that it measures how the option's probability of expiring in the money change with respect to spot change. Also, for a portfolio of options, gamma measures the overall portfolio's delta change when spot changes. Next Greek is vega. Vega is the sensitivity of option price with respect to implied volatility change. Vega of 0.1% means 1% increase in implied volatility will cause option price to increase by 0.1%. For example, for a 1-month call option on Apple with strike $105, option price is at 2% of spot with vega 0.1%. Assume Apple is at $100 with implied volatility at 24%. If spot stays at the same but implied vol move up to 25%, then the option price will be 2% plus 1 times 0.1%, which is 2.1% of underlying spot. Similar to gamma, deep out of the money option has close to 0 vega. This is because option value is close to 0 and higher implied vol won't increase the likelihood for option to be expired in the money. Thus vega is 0. Vega is at the peak for at-the-money option. Increase in implied vol will increase the potential upside gain for option owner, therefore Vega is at highest. For deep in the money option, it behaves just like long or short the underlying asset directly. Implied vol won't have any impact on option price, thus Vega is 0. And similar to Gamma, Vega is always positive for both call and put. For at-the-money options, longer tenor ones will always have higher Vega. Vega is an important Greek as it measures the impact of implied vol change on option value. Very often, even with underlying spot remain unchanged, option value could change dramatically due to implied volatility movement. Therefore, it is crucial to factor in Vega into option strategies formulation. Long tenor options have higher Vega, thus more affected by implied vol movements. The last Greek to cover is theta. Theta is the time decay of option value. Recall from Chapter 2, option value is composed of intrinsic value and time value. Time value decays day by day to 0 and option value will eventually converge into intrinsic value. Theta of minus 0.1% or minus $10 means 0.1% or $10 of option value decay every day. For example, for a 1 month 105 strike call on Apple, option price is $2 and theta is minus $0.1. Assume Apple is at $100 now. If Apple price stays at $100 tomorrow, then the option value tomorrow will be $2 minus $0.1, which is $1.9. In modern day trading system, some simple models calculate theta with calendar day decay, while some sophisticated models use trading calendar decay. Similar to Gamma and Vega, deep out of the money options have 0 theta, as option value and time value are both close to 0. Theta is at the peak for at the money options. This is because at the money options have the highest time value, thus more time decay every day. For deep in the money options, theta is also 0 as option value is just the intrinsic value with time value close to 0. Theta is always negative for both call and put as time value is always positive and decay over time. For at the money options, shorter tenor ones have higher theta. Theta gives traders the idea of how option time value decay every day. Remember, when we buy option, the clock is ticking as option time value decay over time. The decay is not linear over the life of options. Time value decay faster for shorter tenor options, and time value decay slower for longer tenor options. As summary, option Greeks are measurements of some important properties of options. Here is the summary table. Delta is option value change with respect to underlying spot change. Gamma is option delta change with respect to underlying spot change. Vega is option value change with respect to implied volatility change. And theta is the time decay per day. This concludes Chapter 3. Like, subscribe, and visit Ito Analytics website for more option-related materials.